We're going to go live here in 1 second. Speaking of waiting to start up.
Okay.
Yeah, I need to get one of those made. I need to get some in-ear microphones as opposed to just this great big, thing just dangling down beside me like a ruffian. I put it behind my back. There you go.
You
That's
could. That's what they
professional.
do on TV.
And but then my the interface to my audio's a little busted. Can't win. Or you can with your little AirPods.
I actually have so many sets of wireless now, it's not even funny. I appear to be collecting them.
Like Bluetooth headset?
Yeah.
Specifically AirPods or other technologies?
So I have the original AirPods, the new AirPod Pros, which are worth every friggin' cent.
Yeah.
I have my Bose Bluetooth that you can also plug in, so they're perfect for
Mm-hmm.
travel because you can still use them on airplanes. And then I have 10 million cheapy around the neck in the ear Bluetooth for bike riding.
I use Jabras.
Hmm.
Um,
Are those the 9 hour ones?
they're 65 P's, I think. I forget the exact number. Elite 65T, but I think there's newer ones now. And you can often get them at Costco. They're
Mm.
fantastic. Like the thing that yours don't do is they've got the little soft silicon
The AirPod Pros have that.
okay, yeah. So it goes in your
Yeah.
ear and blocks the noise. And so you can
And the
actually
AirPod Pro have active noise cancellation.
oh well, the newer versions have the active noise cancellation. But it's we've had this conversation before, right? I tear earbuds to pieces, and I've gone through. I mean, we've both worn the collars around our necks with the
Yeah.
the LG uh, dongles going into our ears, and these are the way. These are the way. So if
Yeah.
you're not in the Apple ecosystem, then go these Jabras. They're great. And I'm now at probably a year of using them for probably hours every day. And what's great about them
Yeah.
is the little case is a recharger. So you'll
Right.
wear them and then they start to run out of batteries. You can, after some enormous amount of time, like I only run out of batteries when I'm on some big long flight. And then I'll take them out of my ears for half an hour, leave them in the little box, and then I've got the rest of the flight. So,
See, this is why I have three pairs because inevitably one can't be found.
yep.
And then I will wear one until it's completely depleted,
Mm-hmm.
switch to the other while the one charges. So I always have multiple options.
Yep.
And I have one pair that's over ear, my Bose, and then the two that are in ear.
Yeah.
So if none are missing, I can also like
Yeah.
pick how to not like destroy and callus the. You can get calluses in your ears, and that is wrong.
I'm sure I've done that. And then I go with the Sony MDR 7506s for just like good headphones. So if I'm looking to like
Yeah.
hear good sounds in my
I have
ear
my
holes,
ancient Sennheiser ones.
yeah. Yeah, these are these
These,
are great. These are like these are like studio quality, but they're on the cheap. Like they're like $100, which if you can spend $100 on a set of headphones, I
yeah, I
highly
don't think
recommend
these
these.
were that little. These are the Sennheiser PC 350s.
Yeah.
And they're so old that like the earpieces are like you can just look at them and
Yeah.
be like, "Oh, that's old."
Yeah.
But they're actual leather, so me and my latex allergy are happy. Sony's I'm allergic to.
So for some reason, the pop-out chat doesn't actually work on my computer anymore. So I'm going to say hi to. I'm going to have to look over here to see the chat now. So hi to Andy Cowley and Astro YYZ and DPI 209 and Gede Gabriel and Giselle Sabarin and Graham W, Gita Bibra, Jason Lord, John Suffield, Johnny Zed, Lillian Brennan, Pick and Duck, Rich Wilson, Thomas Treneker, Umu, Watermelon Felon, Wayne Johnson, X the King Guard, and Zapvan Zapvan. Hey everybody. And again, a reminder, after this episode of Astronomy Cast, you should come and join me on my YouTube channel for a live premiere of my new episode all about the Daniel K. Inouye image of the surface of the sun, which is just a phenomenal telescope. And we're talking about that next week here on Astronomy Cast, right? But it really feels like this was like one of these monster mega telescopes that just snuck through the radar. And, you know, we've been so busy focused on
because it's solar.
Still. I mean, that first image was absolutely stunning, but the next image is going to look kind of the same, and every other image after that is going to kind of look the same. So, you know, I mean, there'll be some great sunspots and some interesting other solar activity, you know, but in general...
I wonder if it's going to be able to see any transits.
Oh, sure, it would. Yeah.
So, but like, are there any that line up in the coming years?
Oh, there's a couple of Mercury transits every decade. So
yeah, but when's the next one? Because I want to see a transit.
We just had one.
I know, but I'm impatient. I know we're not going to get Venus.
No, we already had our
dead.
shot on that. Yeah, I mean, we'll be into our second robot bodies at that point. November 13th, 2032. So there you go.
I'm displeased by that.
Yeah. Well, you know,
hopefully there'll be something else interesting that
you I feel like you really enjoyed the transit back in 2012. Yeah, we did a great job.
Cool.
We were all over it. We saw it. We streamed it.
I projected it on that wall.
We lived it.
On the other side of that wall.
Yeah. What could sure, it would have been neat to see it on that other telescope, but still, like it's just been a big black circle, right? Come on. With maybe like an atmosphere riddle. Okay, it would have been pretty cool. All right. Okay. All right, so if you're wondering what it is that you have stumbled into, this is going to be a live episode of Astronomy Cast. We are going to record our episode all about a supernova. It just won't stand. It won't happen. It's going to have to go in front of me. I apologize. All right. We will record the show, and then, it's all about Supernova 2006 GY. We'll record the show, and then we will stick around for your questions about space and astronomy until around 1 o'clock. So,
what's the episode number?
558.
Okay. There needs to be like an Astronomy Cast bingo of me asking that most weeks.
I'm sure it exists. I'm sure someone's working on a supercut right now.
All right.
Are you ready?
Yep.
Here we go.
Pressing record.
I've also pressed record.
And recording.
All right. Astronomy Cast, episode 558. Finally explaining Supernova 2006 GY. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser, Cain, publisher of Universe Today. With me, as always, Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing?
Doing very well as well. Anything new happening in the your verse? The CosmoQuest verse?
Snowing?
Yeah, we've had a few extra snowfalls too.
So we are plugging away every winter's day on our new code set. One of you out there, you know who you are, actually came over and joined us on Discord to help us out with the coding, and that made me super excited. So if any of you want to donate some time and join our open source project, we're doing a complete rebuild, and you are all welcome, and I get super happy if you say you understand JavaScript.
Complete rebuilds are always fun, and by that I mean never. We've been following this story for more than a decade, so it's great to finally have an answer to the question, why was Supernova 2006 GY so insanely bright? Astronomers originally thought it was an example of a supermassive star exploding, but new evidence provides an even more fascinating answer. All right, Pamela, do you remember where you were when supernova 2006 GY exploded? It was actually before our time on Astronomy Cast, wasn't it?
Yeah, so I would have just moved here to Illinois. I would have been a baby professor. We would have just started this show. This was an end of the year supernova.
Mm-hmm.
And so I don't know exactly where I was, but it wasn't too far from here.
Um, I don't remember the story. I had to go and look in the archives at the time when we reported on it, and then all the various updates that we reported on this
Yeah.
story. And it's one of those things, though, where when you do kind of look back at the story with all of the knowledge that we now have, you can see the whole thing unfolding bit by bit. And so back in 2006, as you say, at the end of the year, astronomers saw a supernova that was unlike anything that they had ever seen. So, what was wrong with it?
Well, not necessarily wrong, but the thing that was initially fascinating about it is it was just way brighter than we had previously seen. Once you corrected for distance, it had the highest luminosity up until that date. So, with massive amounts of energy coming out of it, and with a crazy light curve, it was initially assumed that this was what's called a type 2 supernova, the explosion of a massive star that's going to leave behind a neutron star or black hole. But different kinds of supernova are supposed to increase and decrease in brightness in very set ways. And while this started out looking like a type 2 supernova, it didn't stay looking as type 2 supernova.
So let's talk. I mean, we've done whole episodes on all the different flavors, but let's go back and give people the quick overview of the different kinds of supernova that you can expect to see out there.
So broad physics case, you have supernova that are single stars that are generally massive, and when they run out of fissionable materials in their core that can generate new energy, they stop producing light pressure that supports the outer layers of the star, and they collapse under gravity. And all of that collapsing material triggers a new round of thermonuclear reactions. The star now explodes outwards as a supernova. So that's one model of behavior. Now, the other model of behavior is you have something like a white dwarf that is made out of what we call degenerate matter. A white dwarf is an object roughly the size of the Earth that has the mass of the sun. And when you cram all of that mass into so small a volume, you end up with the electrons having to arrange themselves in a very specific way to avoid breaking the Pauli exclusion principle. So all of the electrons are like, okay, you be in this level, you be in this level, we'll spin in these particular ways. And this electron degenerate gas is as tight a gas as you can form out of the electrons. And if you compress it too far, the electrons can no longer support each other. Pauli exclusion principle breaks. Those electrons and the protons they're associated with end up merging and forming neutrons. Everything goes badly. There's a lot of energy released. And this is the other way you can get a supernova, is by piling too much mass on one of these electron degenerate gas white dwarf stars, defying the Pauli exclusion principle and exploding that white dwarf. That's a type 1a supernova. Now, in general, because type 1As all detonate at the same amount of mass, they're supposed to be the same amount of light. Now, the names for those massive stars that are exploding are all over the map. There's type 2, there's type 1c, there's all these different letters added on, but they're all massive stars.
So okay, so just to sort of follow the mystery, astronomers saw what was the inherently the brightest supernova they had ever seen.
Yes.
but so then it couldn't have been a white dwarf because they're not that bright.
Exactly. At least that's what was initially
Right.
thought. So you have their initial thinking, and I'm going over this so that I can make sense of all of this later because no physics is harmed in this episode. So you have a white dwarf worth of energy tied up in the mass. And that amount of energy, when it goes boom, always releases
Right.
the same
Right.
amount of energy.
And the sort of example, right? I mean, essentially, it's like one big diamond the size of the
Yeah.
Earth. It is this carbon, as you say, this carbon lattice. And the moment it crosses over this line where the thing collapses inward, the whole thing just turns into carbon burning, and it's just gone. Like kaboom,
Yeah.
and it's gone because the whole thing suddenly. A lifetime's worth of fusion happens in an instant. Every atom in the entire star proceeds to do carbon fusion, and the whole thing just goes kaboom. And you get this wonderful standard candle that astronomers use to measure the size of the universe.
And these different kinds of supernova all give off their own signature display where you get one set of elements being brought into creation by a type 1a, another set of elements being brought into creation by a type 2, by type 1c. All these different kinds, because they have distinct nuclear reactions that go on, produce a distinct set of elements and also related elemental lines in their spectra.
Right. Okay, so type 1a supernova, exploding white dwarf ruled out. So now we're looking at a type 2 supernova, but why did they not think that it was a core collapse supernova? Why did they think it was something? I mean, it was more energy than the brightest supernova that had ever been seen. So couldn't that just be like a monster star that core collapsed?
Well, so they initially did think that it was a monster star that had core collapsed. Now, the issue became a few hundred days after its initial explosion, when they were looking at it, what they saw was it had one decreased in mass, not mass, decreased in luminosity in ways that didn't match with their type 2 model. The other thing that they saw was the spectra had a bunch of really weird atomic lines in it that for a long time scientists couldn't figure out. And it's only in a recent paper by Anders Jerkstand, Kichimada, and Koji Kamabata that they were able to piece together that these really weird atomic lines that were coming from the area of excited material around that supernova explosion were neutral iron.
Okay,
And,
what's wrong with neutral iron?
well, neutral means that your little happy iron atom hasn't had any of its electrons stripped off. And you're always going to have some of that hanging out around a supernova, but the strength of these lines corresponded to half a solar mass or so, between a third and a half a solar mass of iron in the vicinity around this star. And that amount of iron at the temperature that made sense with neutral iron isn't something that you're going to get with a core collapsed star. The
Okay,
temperature was wrong.
right. And so astronomers now had to, because originally they were thinking that it was something like at a Carinae, right? Like there was going to be this
Yeah.
star with 100 to 200 times the mass of
Yes.
the sun had exploded. And as you said, they looked at it in it was visually bright, but like when they looked at it with say the Chandra X-ray Observatory, it wasn't intrinsically X-ray bright in the way that you would expect one of these monster stars. So it's always this mystery. Okay, so now you see all this neutral iron in the vicinity. So what does that mean?
Well, so that seems to imply, well, expletive. The only way you get that is with that type 1a supernova that we were talking about.
Wait, we just ruled that out.
Right. And this is the problem. And this is a very short and brilliant research paper that pieced together a lot of the research about this to come to a really clean conclusion. So looking at this and seeing, wow, there must have been all of this material that came out of this. How do you do that? What is the temperature that corresponds to it? Well, what they looked at was, and here I'm going to read from the paper, a core collapse supernova would produce too little, and I'm paraphrasing, too little nickel. It would only have produced a tenth of a solar mass of nickel that would have then decayed via cobalt to form that iron. So it can't be that. And it couldn't have like expelled that much mass. And so if you instead look at, well, what about a pair instability type explosion? Well,
Which is
there
a
you would,
variety of those super mega heavy stars where they go through a
right,
different kind of, essentially, from what I understand, it's like they get to a point where they contract inward almost in a moment and then bounce as a supernova and tear themselves apart completely.
right. And to get what they were seeing would have required a 90 solar mass helium core.
Right.
And that's not a thing really.
Right. Okay.
So that didn't work. So how do you get this much energy out of a white dwarf, which is the only way they could explain the amount of iron they were seeing?
Okay.
Well,
Okay. What do they propose? What do they think happened?
kinetic energy.
Kinetic
So
energy.
you have all the energy that is in the mass of the star. That's contributing to the supernova. That's what we're used to in the type 1A. But if you have a fast moving white dwarf star that has kinetic energy, this is the same kind of energy that causes massive craters to form when asteroids strike objects. It's that kinetic energy getting transferred into other forms of energy that causes things to go boom. Well, in this case, what we're seeing is a white dwarf in a binary system that is undergoing a merger. So here it's like we're going to pull out every possible bell and whistle to make this happen.
Right. This is the most extreme, bizarre, crazy system you can possibly imagine.
This is awesome.
Yeah.
And as the white dwarf um, goes into the envelope of its companion star, which is just a like regular giant star.
Right. Like a red giant star. Like what our
Yeah,
sun will do when it dies.
it is able to shed out all this material from the outer envelope to make a tight uh, circumstellar medium around the star.
I'm imagining like a car tire going through a mud puddle,
So,
right?
or the way I
Right? Or
imagine
just
it,
like spraying out water as it's just carving through this puddle.
so maybe because I'm a woman, I think of it as stirring something too quickly and you spray material in all directions. So you have this white dwarf plowing through the outer layer of its companion. They're now like a single shared envelope system. It's in the process of merging. And somewhere along the lines, this white dwarf star is like, and there is too much mass on me.
Right. But that's what they do, right? I mean, that's how you get a type 1A supernova is you feed a white dwarf 1.4 times the mass of the sun slowly, carefully, and then it finally explodes. But in this case, it was force fed as it dove through the
And it
envelope
got
of this
so
red.
much angular momentum,
Right.
so much angular momentum.
Right.
And it's the transfer of angular momentum and the shedding of its orbital velocity all of this energy was where all that excess energy came from. And so this raises this fascinating, well, expletive. Part of the variation that we're going to see in type 1a supernova is going to be driven by, are they, what is their velocity energy that they're getting rid of? What is this kinetic energy that's going into these explosions?
Oh, so you think
And
this might have implications for using white dwarfs as standard candles just in general?
yeah, so
Interesting.
one of the things they hint at is this could be an explanation for other weird supernova we haven't been able to understand. And if we're seeing on a regular basis, by which I mean, if it's astronomy, if you see something 6 times, it's a trend. So if we're seeing this ever so rarely with this huge and dramatic effect, how often are those small deviations from the mean caused not just by the environment that the star is in, but by also the energy that is in the star system? We know all of these are binary. That's how they happen.
Right. Right. We know that white dwarfs exploding as type 1a supernova, which is this standard candle, they are all a each one of them is, as I said, you're sipping away at some other star's juice, and
And
eventually you
and
explode. But I
and so
mean, oh, go ahead.
if you start with the idea that a standard candle means every single one of these should explode with the same luminosity, the same number of lumens, that same candle brightness. But then it turns out that sometimes they have this secondary source of energy. That adds a fascinating source of noise.
Right.
And so
Absolutely.
I love the implications of this research.
Right. And so when you think about how astronomers are using these standard candles to measure the distance to various galaxies across the universe, and of course they're finding that these stars are farther away than they should have been, then this is dark energy. I mean, this whole idea of dark energy. Although, I mean, it's exciting, but then at the same time, you'd expect it to be random, right? There wouldn't be some
Yes.
reason why the stars that are farther away are extra far away while the stars that are closer are not. Like that, you wouldn't have that direct correlation between them
Right.
feeding in strange ways, but you would definitely, it could definitely have an implication on just your understanding of how bright these standard candles are.
And and this is a random source of noise. And you have to assume that while it may not be equal on both sides of the skew, um, there's probably not a reason that it would change over the history of the universe. I wouldn't be surprised if we see dark energy go away as our research evolves, because we are finding that there are systemic effects uh, where the populations that white dwarfs are forming from change over time. And we're starting to see hints that different populations of stars produced white dwarfs of different luminosities. This isn't the effect that's going to make
Right.
dark energy go away. This is just going to create noise in our measurements that is going to make measuring those
Right.
other effects that much more difficult.
Right, but it is going to be awesome noise. So just to sort of like rewind and sort of understand this story, right? You had these two happy stars in a binary relationship, two main
Yeah.
sequence stars. One was a little more massive than the other. And at some point, the more massive star died, bloated up
Yes.
as a white dwarf, puffed out its outer layers, and then puffed out as a red giant, sorry, bloated up, threw out all its outer layers, and then collapsed down into a white dwarf. And I guess by doing so, sort of changed the gravity dynamics of the system. And so now you've got a white dwarf orbiting around a main sequence star. And then X billion years later, the second star puffs out as a red giant, eats the white dwarf, The white dwarf just careens into it, gobbles up enough mass, and apparently it only took like 100 years. Like when
Yeah,
this
that's
actually
the
happened,
awesome part.
yeah, and then it gathered, wrecked the star. So it's not like it sort of plunged in and just sort of gently faded away down to the core of the star. It just, like I said, like a car going through a mud puddle, or, you know, someone mentioned in the chat, right? Turning on your blender with the without the lid, and
And what's kind of cool is they can actually use that iron, the iron lines keep being so important. So they were able to figure out when the circumstellar material must have been emitted to get all the velocities of everything going correctly. And so they figured out that that must have been emitted in the past 100 to 200 years. So that actually, they went from thinking that the merger took between 10-ish order of to 200-ish order of years. But then you look at that iron and that material that would have been created by the infalling white dwarf, and that tells you that this was a hypergiant because of the infall times for the different kinds of scenarios. So they were able to figure
good
out what the
work.
white dwarf fell into
Yeah.
by when that circumstellar material was put into place.
And so when you've got this white dwarf star exploding in the in the wreckage that it caused as it spiraled into the red giant, then the energy and the material blasting out of this white dwarf collided with this material, and that's what caused the brightness. That's what caused the luminosity, is the collision
Mm,
between the white dwarf and the material around it.
that's what caused the iron that we saw. So the brightness of the supernova came from, you have a white dwarf star that is flying around inside what's called a common envelope. So you have a star that now has two nuclei. One that is that hypergiant, uh, it started out there nuclei, and the other that is this infalling white dwarf. And it is the combined kinetic energy of the white dwarf and the mass energy of the white dwarf that goes into all of the nuclear kaboom parts. That combined kinetic energy and the regular kaboom energy, that's what created
Right.
the
Okay. Okay.
amazing initial luminosity. It radically faded so that when they were looking at it 400 days later, it was 100 times less bright than
Right.
expected. And what they were seeing at that part time was the illuminated material that had been shed,
Right.
which included the neutral iron lines.
So a better analogy might be like when two black holes collide with each other and you get this gravitational waves, and people say, 10 times the mass of the sun was released in gravitational waves. It's not like the black holes got less massive, it's that the kinetic energy of their collisions was turned into the gravitational waves that rippled throughout the universe. And so, in a similar situation, you've got the kinetic energy from this white dwarf spiraling inward that is then able to translate that into additional energy, an extra 1-2 punch for its supernova.
And one of my favorite parts about this paper is I was extremely eager after hearing the question from one of our audience members, Bad Panda Bear. He asked, well, what was the result of this? And in trying to find out, the authors of the paper were like, we haven't been able to model situations like this.
Right.
They're just too complicated.
Like, did the
And
red giant exist after the white dwarf exploded?
can't tell yet.
Yeah.
And so this is a class of objects. This isn't just one object. This is a class of object. Shared common envelope systems, merging binaries that go boom. And in some cases, the going boom is going to be mediated by gravitational waves. In some cases, it's just going to go boom. And trying to understand the timing of this, how quickly they go, how slowly they go, what's left. We need better computers.
Yeah.
So there's still more to come on
Right.
stories like this. We don't yet know how this one ends. We just are understanding how it began.
Or way bigger telescopes, because this thing is tens of millions of light years away. So
Well,
there's no observing it, right? There's observing the explosion, but you can't point a telescope with that level of precision to see what's there now or what was there before.
once the nebula gets a little bit bigger, you'll be able to see what's left in the
Oh,
center.
good
We're
point.
just not there yet.
Yeah, yeah. So James Webb, this will be one of your future targets. But it's great
Oh,
when
you're
you
so
think about
optimistic.
it's gonna launch. It's so great when you think about just all of these different combinations that there are. You can mix and match black holes, neutron stars, white dwarfs, red giants, supergiants, in every combination.
Black
And
holes do not form common envelope stars.
no, but they sure can. What happens if they hit one, right? Like, I mean, the point is something is observed when
Yes.
these monsters interact with each other.
Yes.
And so right now you've sort of got, on the one hand, you've got this, imaginary collection of different ways these different objects can come together, and on the other hand, you've got all of these observations that are across this entire spectrum of what people have seen. And it's like this, it's like this mix and match where you're like, okay, is this that? Is that this? And so I look forward to them continuing to try to figure out which causes what. It's like a
And the cool thing that we're just starting to statistically learn, and this is the last cool thing for today, I promise. Uh, we're finding that more binaries than we used to think become binaries late in life. So you can have systems that have an evolved low mass companion and a not yet evolved high mass star.
right.
And so, this potential of having white dwarfs around truly massive stars is going to lead to even a larger diversity of objects being possible.
So cool. Pamela, do you have some names for us to
I
celebrate here on Astronomy Cast?
I do. Astronomy Cast is entirely a listener supported podcast. We are here because of you and your patronage on patreon.com/astronomycast allow us to pay our servers, pay our software, and pay our Susie. So thank you for everything you do. And this week, I'd like to thank Brian Kilby, Jessica Feltz, Omar Del Riviero, William Lauer, Joe Wilkinson, Bruno Letts, Marco Lorassi, Dustin A. Rolfe, Mark Grundy, J. Alex Anderson, Jeremy Kerwin, Mark Stephen Razdak, Tim Garish, Paul L. Hayden, Brent Kranop, Iran Segev, Arthur Latz Hall, William Anders, Jack, Joshua Pearson, Justin Proctor, Frederick Saj, Claudia Mastriani, Rachel Fry, David Gates, Dwayne Isaac, and Thomas Tubman. Thank you all. You make us happen.
Thanks, everybody, and we'll see you all next week.
Bye-bye.
All right.
Now don't actually go anywhere.
No, that's just
We
for
will
the
answer.
people who listen on the podcast.
Yeah.
You get more. Like the thrilling content of us saving our audio files and
Well,
uploading
yeah.
them.
It's true.
This is fun. Okay.
We will be with you in a moment, everyone.
Okay. I'm safe.
Okay, so am I.
All right. So hit us with your questions. And again, I apologize. I can't move the chat window over here. I have to look at it over there, which is so dumb.
Sometimes even the
Maybe I
best
can
of
do
technology
this.
fails us.
Nope. Can I do this? Maybe? Okay. Well, this will work. I just can't see
Okay.
my screen. Let's see. So has anybody got any questions? Okay. Paul Gracie asks, could it be that the extra brightness that we see is due to a much greater energy in the vector direction that we are seeing it? I guess it's kind of like that idea with gamma ray bursts, right? That that we're seeing it because it's like maybe the energy is being funneled down this cohesive beam that's being zapped at planet Earth.
So the nice thing about a system like this is because it's surrounded by all of this material, we have to match that energy radiating away in all directions, not just the radiation coming towards us. And the way they were able to match the radiation coming towards us as well as the radiation hitting that circumstellar material was with a uniform model that had this type 1A supernova with all sorts of kinetic energy.
Bill Nash asks, when black holes collide, is there any possibility of an ejecta? What would it look like?
Say that again?
So when black holes collide, is there any possibility of an ejecta? And what would that look like?
No.
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 No,
No.
nothing comes out.
Not going to happen. Gravitational waves.
Yeah,
That's it.
that's
That's all we got, folks.
Yeah. Yeah, nothing can escape a black hole, not even wreckage.
Now, if you have two black holes with two separate accretion disks, which can happen if you have two active galactic nuclei coming together with the merger of two galaxies, then you can end up with all sorts of shock waves and balloons of material and cool stuff. But that's the accretion disks, not the black holes.
Lillian Brennan asks, so how long have they been working on James Webb and when should it have originally launched?
2010. It was supposed to launch in 2010. And it's gonna get delayed again.
Yeah, by 4 months.
Yeah. So talk to CosmoQuest's Annie Wilson, Binary Blaze, the wonderful woman hosting this currently over on Twitch.
Yep.
She read the most recent General Accounting Office report so that the rest of us wouldn't have to.
Thank you, Annie.
There are over 350 single points of failure and mismanufactured bolts that they have to figure out which bolts need to be replaced and which don't.
Yeah, so if you missed it, Annie went into great detail on this week's episode of the Weekly Space Hangout and just described with horror the reading that she had done on where things were at, and just, some part had been installed upside down, which is the kind of mistake that we make, when we buy some furniture from IKEA, right? We always do that. But apparently this had been done on the James Webb Space Telescope, as well as you said, there was a batch of bolts where many of them were faulty. And now they have to figure out, they can't just replace them all. Nobody's got time for that, but they've got to figure out which are the ones that could bust. It's going to launch. It's going to launch. It's going to launch. It's going to launch. It's going to happen. Don't worry about it, everybody. It's just an extra 4 months.
Here's a question for you from Bad Panda Bear, Fraser.
Mm-hmm.
Bad Panda Bear is asking, when is the new Event Horizon telescope image of the center of the Milky Way going to come out?
We don't know. Yeah, we still don't know. They took the picture for M87 and the center of the Milky Way at the same time. And from what I was able to understand back when they released the M87 picture was with M87, it's a much bigger black hole and it's much farther away. And so it's rotating on the order of weeks to turn, while the one that is rotating at the center of the Milky Way is orbiting on the order of minutes. And so the environment around the black hole is a lot more dynamic and a lot more complicated to try to tease out the data in the image. And so it's just it turns out that the bigger black hole was the
easier.
Yeah, it was easier. Was the practice run for them figuring out how to do the bigger version. So
and the key piece of information on that to me was the size on the sky of the M87 supermassive black hole and the Sag A star supermassive black hole. They're about the same angular size. And if you think about vast difference in distances to these two objects. That means that the intervening material is huge comparatively for our galaxy.
Yeah.
And I'm getting a correction on the bolt situation. Arnstra, who works in satellites,
Hmm.
writes that there are 501 incorrect bolts,
Yeah.
i.e., bolts that in and of themselves they were manufactured perfectly, but were used in the wrong place.
Oh, okay. All right. So the bolts are fine. They're just the wrong bolts.
And Stella knows I'm upset.
Aww.
so
Stella's just
so
trying to
much.
tell you that that telescope will launch. Um, uh, Someone was asking, yeah, Rituals wants to know which will come first, the picture of the black hole, the Iowa results. Um, so Uncle Bill Druin says, just how standard are these standard candles? Seems like there would be some statistical variation.
There is. So the goal is how close to are the errors such that we can actually see dark energy? Um, are the errors such that the deviations from what we'd see without dark energy uh, are greater than the error? And if you see enough supernova at the same distance, by seeing so many at the same distance, it starts to, the statistics allow you to reduce the noise. It's messy,
Yeah.
um, but it appears currently, if you assume that there is no difference in the typical supernova brightness as a function of environment, then the deviation is greater than the noise.
Right.
But if there is a difference as a function of environment, all bets are off.
Right. And this is, I mean, dark energy is such a bold and bizarre discovery and prediction that it absolutely makes sense that if you're basing your entire prediction about the future of the universe on the fact that type 1a supernova are a standard candle, it's worth going back and trying to figure out exactly how your standard candles work to standardize your standard candles. And so a lot of work is being done, especially now on just, are we absolutely sure that all of these supernova exploded with the exact same brightness? And
And
and the
and
work continues.
yeah, and there's some really intriguing results
Yeah.
looking at different chemical environments.
Yeah, I mean, I think the most fascinating possibility is there's one result that is saying that actually dark energy isn't even necessary anymore
Right.
because it's possible that essentially what type 1a supernova were made of, and you mentioned this sort of earlier on in the episode, that what they were made of evolved over the time of the universe. And
Yeah.
so young supernova, type 1a supernova that were formed 3 billion years after the Big Bang had a different chemical structure than the ones that formed more recently in a way that actually makes dark energy completely go away.
And it's even more trickstery than that because different galaxies formed at different times. And so you can have two galaxies at the same point in time that have completely different chemical compositions.
Yeah.
And because they have different chemical compositions, they'll have different kinds of supernova. But on average, the average chemistry of galaxies has evolved with time, so that there are extremely few metal poor galaxies today, and there were extremely few metal rich galaxies in the past. So, as the average of the universe has changed, you've seen the average luminosity of the supernova
Right.
change if this result is correct.
Yeah.
And so far, they've only looked at select kinds of galaxies and select supernova. So significantly more work is needed.
Yeah.
But
It's a great
this is the
start.
thing to watch.
Yeah.
And it's going to be interesting to see if this is a result that anyone can even accept as long as the people who won that Nobel Prize are alive. Because
Oh,
there's a long history in astronomy of new results not being accepted until the right person is dead.
right,
And I'm hoping that's not the case.
right. Um, I mean, this is like if it turns out that dark energy wasn't a thing,
Yeah.
right? How will you
The
feel?
math is so much easier.
Yeah, like how will you feel?
I will be overjoyed.
Right, right. So right now, do you think that dark energy is a real thing?
Right now, I would lay bets that it gets disproved in my lifetime.
Really?
Yeah.
Yeah. I I doubt that. It still does feel like a real thing that, the preponderance of evidence right now seems leading towards it being a real thing. But I guess the point is like it doesn't matter, right? Like
Right.
like the reality is just
It's what the
reality.
data
Yeah, and so
shows.
if it turns out that it's not real, then great, we throw it out. And if it turns out that it is real, it's super real, then great, we keep going. I mean, we have plenty of examples of things that are super weird and uncomfortable that are real, like quantum mechanics. Every aspect of quantum mechanics just is weird, and yet it's real to a level of precision and accuracy that almost no other kind of science has ever been able to make those predictions. So, people always say that scientists aren't open-minded, but like totally are.
We're also grouchy and emotional.
Oh,
So we are rational, grouchy, and emotional all at the same time.
right.
And I guess that makes us human.
Yeah. Yeah. I mean, just like human beings, yeah, you've spent all your life trying to prove that volcanoes killed the dinosaurs, and as the evidence mounts that it turns out it was an asteroid strike, you're going to be a little upset.
Yeah.
Ideally,
So
not. Ideally, you're like, woohoo! I don't have to work on this anymore, right?
or woohoo, my math is so much easier, which
Yeah.
is how I feel about
Yeah.
this particular
Exactly. Yeah.
situation.
Yeah.
But I have one final thing that I just realized today is the correct time to say. If you are looking for something sciency for Valentine's Day, which is next week apparently, the necklace I am wearing is one that I made. I make planet
Oh,
necklaces.
that's cool.
So check out 739studios.com and get some science for your loved one.
Ah, that's so sweet. Um, Appel J asks, is there can people donate without Patreon? So let's say you want to support
Oh
Astronomy
yeah.
Cast and you
Yeah, go
and you
to
don't want to do.
astronomycast.com/donate
Yep.
and PayPal.
Yep.
We just can't send you all the cool benefits the
Right.
same way. So if you're on Patreon, you're going to get extra emails, you're going to get just
Office
random other extra
time.
things.
Yeah. I
But
mean,
if you just want to throw money at us, we're not going to stop you.
no. Um, or you can sign up for Patreon, give for 1 month, and then cancel your account again, or cancel
Yeah.
your donation again. Right. The
Yeah.
thing. I mean, you and I both sort of triggered on a tweet that happened a couple of days ago,
Right.
that Patreon just in general for us as creators, as people who are
Yeah.
professionals who intend to show up every day and do the work.
Yeah.
Patreon's a game changer because
Yeah.
it allows us to match the cash flow with the work that we do. I mean,
Yes.
imagine if you did a job and sometimes people would, you'd have some months where a bunch of people gave you, your employer so it's like, here's some money for you. And then other months would go by where your employer's like, you know what? No money for you this month. And you'd be like, well, I've got to eat and I've got to, you
I've
know,
had that month.
I used to have those months all the time, right?
Right.
And now I have 850 people who contribute every month to what I do with Universe Today, and what it allows, and it has allowed us to settle in on just a regular repeatable schedule that
Yeah.
everyone who's in my organization has their jobs that they do, and we can run the machine at a pace that
Yeah.
has never existed before for us as creators. It has always been this feast or famine world, kind of like you getting, filling out
Federal grants.
federal grants, right? And so something like
Yeah.
Patreon, and so just in general, like if you have some kind of like philosophical problem with maybe some of the people that Patreon doesn't fund, I hope that overweighing that is just the level of peace and safety that it gives the
Yeah.
creators that you love, who you want to show up, who if they didn't show up because they had to go and get regular jobs because it was the famine portion of that cycle, that you would be
Yeah.
sad. So
Patreon is the only reason I'm still in astronomy.
yeah,
And that sounds like
yeah,
a huge sort of flamboyant statement, but it's the God's honest truth.
yeah,
I'm lucky enough that I am married and my husband pays for our house that is way
yeah,
too cold in the winter. But I'm still responsible for some of the bills around the house. I still have to pay all my own server charges, my cell phone. I bought a new wool sweater the other day because the wool sweater is cheaper than the heating bill. And I couldn't do any of that if it wasn't for that income that I rely on every month from patreon.com/starstrider.
yep,
The rate at which I sell necklaces like this is completely random. And there have been months where it's like, woohoo, new slippers. Yes, that is how check to check I am. Um, but that month after month, knowing
yeah.
that there's just that amount coming in on Patreon that will cover my basic bills
Mm-hmm.
allowed me to not have to go find a different job.
Yep. Yeah, no, absolutely. And I hope that people have enjoyed the regular content that they've been getting from both what we do here on Astronomy Cast, and even just what we've been doing over on Universe Today. Like people,
Yeah.
I think, know that they can feel that we are able to be professionals and do this work, and that is entirely due to Patreon. So, speaking of work that has to be done, we should wrap this up because I've got a premiere happening in 1 minute over on my YouTube channel. I hope someone can post a link because I'm now logged in as Astronomy Cast, and so I can't actually even access my link. So, but if you go search for Fraser Cain on YouTube, you can come and watch the brand new episode, the one that I got like 10 people disliking the video before I even launched it because it was a premiere. So come and watch it. I think you'll like it. It's one of the best episodes that we've done. So come and enjoy. And otherwise, thank you everyone for watching. Thanks to Susie. Thanks Pamela. Thanks to the moderators. And thanks to everyone who
Thanks to
supports the
Annie
work
over
that
on
we do. Thanks to
Twitch.
Annie for reading the James Webb document so we didn't have to. And of course, responding to all the comments over there. We will see all of you next week. Thanks, everybody.
Bye.